Hey guys, how we going? This is financial modelling, which is our unit for the first kind of 4 weeks of term two. And it's looking like towards the end of this unit is when we'll be coming back to school, at least some, if not all, of year 12. So this is kind of our working from home unit. Again, we've done it this way because it's the best thing to be doing kind of independently. It all kind of makes sense, it clicks, it's useful in real life, and it's all just patterns. It can be a little bit fun. So we've got a new intro, we've got a good topic, yet to see this smart face. Term two, let's do it. So the first thing I kind of want to draw your attention to is the why. Why would we care at all about financial modeling? The truth of it is we're starting with sequences and series, which is basically like the x plus 3x of algebra. Like it's very basic beginnings, and the stuff we're doing isn't going to be that applicable in real life. But it's the building blocks that later down the track, if you do this at university, if you do any kind of like accounting or mathematical modeling in your tertiary courses, then this is where it's so ubiquitous in everything that we do. So, for example, this man here, Josh Friedenberg, I don't know how to say his last name, is our current treasurer in Australia. And so he's obviously been a big part of all of our financial decisions. And if you think any decisions over this past couple of months have not had to do with finances, you're kidding yourself. Everything comes back to the economy and how we're going to come out on the other side. Okay, so for an example of that, if you think about our free childcare program, okay, so the whole idea was that rates were paid to parents, and you might think, well, that's a really sweet, it makes sense, it's a great program, and it is a great program. But the financial modeling side of that is that getting those parents to have their kids back in childcare means that childcare workers are then employed and they have money and they're able to contribute and put money back into the economy. And the same way with essential workers who are stuck looking after their kids can get back to work as well. And again, that means more shops open, more money in their pockets, more money getting into the economy in Albury and all around Australia. Okay. The idea is a little bit of a cost gets a whole heap more money in the economy. And then all those people are hopefully off job keepers and job seekers and all these government payments, which again frees up more money. So that's an example of it was not an overnight decision. There would have been a lot of thought and modeling that went into that. And that's how they kind of model government decisions based on how over the long period we can end up more financially good. So in terms of the basics, we're going to start with sequences, and sequences are really nice. It's basically going to be either adding, okay, or multiplying. So if we have a look at this first sentence here, and the way I would be doing these lessons is either if you have a tablet or a computer that you like to use in that way, you can get these as a PDF from the teams, and then you can just fill in the blanks along with me. You might just like to watch along, or maybe you'd like to print these off and write it out. Maybe you just watch along and then you write some notes in your book. Whatever works for you. You generally don't have to write any notes if that's not how you learn. Go through the lesson, and then if you can do the questions at the end, wicked. Okay, so a sequence in which each term changes by adding a constant amount. So when you're adding on a set number, okay, each time, that's called an arithmetic sequence. Okay, think about like arithmetic. It's an arithmetic sequence. That's when you are adding the same thing on every time. Okay, we often call that an AP. Okay, it can also be called like an arithmetic progression instead of sequence. So if you have a look at this first example here, we've got minus 3, 5, 13, 21. Now you can start by saying, well, is that an arithmetic sequence? Is it going up by the same amount each time? It's going up by plus 8. So yeah, it's an arithmetic sequence. Okay. Now this one in particular is called a finite sequence because it ends. Okay, because it has a finish. it has a final term. Okay, it finishes. That's all there is to it. Okay, this one underneath is technically not an arithmetic sequence. It's a different kind of sequence. In fact, it's a geometric sequence, and that's going to be when we're multiplying. We're not looking at those yet, okay? But it's just a different kind of sequence. We're either adding or we're multiplying. Now, this one in particular is called an infinite sequence because of those three little dots, the ellipses at the end, which implies that that sequence is going to go on forever. Okay, so I suppose we'd write here because it goes on forever. Another way you could write that if you want to be more like mathematically rigorous, I guess you could say like it goes to the infinite term. Okay, but I know Meg will hate that, so I won't use that. Okay, so let's have a look at a couple examples here and how to get like some rules and some patterns going. So if we have this sequence 10, 15, 20, 25, we're going to find these two things, A and D. So A, okay, in brackets, is your first term, so T1. It's really easy. All you're going to do is you're going to look at your sequence and your first term is 10. We call it A when we're using sequence notation. So A is 10. Now D is called the common difference. So that's the same as saying, what are we adding on each time? Or what's the difference between each term? So if you have a look at this sequence, I've written in brackets for you. There is like a rule, a method that you can use. You can also just figure it out. But if you use this rule, you can't really go wrong. We're going to grab the second term and we're going to take away the first term. Obviously, you could do that with any two sequential terms. We're going to just do it with T1, T2. You get a difference of 5, which makes sense because we're adding 5 to each term in the sequence. Okay, so now we're going to come to this little table, and what we've got is n, meaning the number of that term. We've got tn, which is going to be the answer at that point, okay? And then we've got the pattern, which we're going to write in terms of our A and our D. And the reason we're doing that is to create a rule that we can use to answer a whole heap of problems when we do arithmetic sequence stuff. Okay, or arithmetic progressions if you see that with the P. Okay, so we can see that our first term was 10 and our pattern is just 10. Okay, our second term is 15 and we get that by taking our first term and adding on the difference, so 5. Our third term was 20, which was, again, we started with 10 and then you've added on 2 lots of 5, 2 of the difference. The fourth term is 25. Again, you started at 10 and then you added on 3 lots of the difference of 5. So if you want to pause this and do it on your own, we're going to fill in these missing values in the table and then do it for the nth to come up with like a general rule, which was already there. So for our fifth term, all we're going to do is we're going to add the common difference. We're going to add 5. We're going to get 30. Okay, and now you need to think about the pattern. So if we started with 10, then how many lots of 5 have I added? And it must be 4. Okay, and then this will be 35, and you've added 5 lots of 5, and 40, and you've added 6 lots of 5. Now, if we did this for the nth term, and that's meaning like if you were to make a rule for any number, n, what would the rule be that you can then use? Okay, so if we do it for n, we're always going to start with this a value. You can see that really clearly. It always starts with 10. So we're going to do 10 being our starting value. And then what we add, okay, is not the number times 5. In fact, it's 1 less than the number, okay? And that's consistent the whole way through. For the second term, you're adding 1 lot of 5. Third term, you're adding 2 lots. Fourth term, you're adding 3 lots, so on, so on, so on. So we need a way to write that, okay? And this is going to be a common thing that we do with sequences in series, is writing it as the n take 1 times Or I'll write it as kind of like times 5. I'm jumping to the answer. So what we did here is we start with 10, and then you'll notice from our pattern that we're going to add whatever number it is, minus 1, that many lots of 5. And that gives us our rule. So if I was to do like t of 4, I'd get 10 plus, now 4 minus 1 is 3, times 5. Don't forget your order of operations. You've got to do times before you do your add. I'm going to get 10 plus 15. I'm going to get 25. Does that check out? It does. Wicked. Our rule works. That's it. Cool. Now, to do that for any progression, okay, so for any sequence, to come up with this rule, we're not going to write out that full table. That's crazy. You don't have the time. What you're going to do is write it in terms of A and D. So remember, A was, like it says here, A was our first term, and D is our